The time has come for us to investigate some other trigonometric functions, or rather inverses of those trigonometric functions. For our fourth installment, we're going to take a look at the cotangent function. So a graph of the cotangent function looks approximately like this. If we take a look at it to the left and to the right of the y-axis. Now the logic that we're going to use to turn this into a one-to-one function is going to be the same as the logic that we used for the tangent function. I'd like to go in between any two vertical asymptotes. I'd like to keep it close to x equals 0. I'd like to work with positive angles wherever possible. So the restriction that I'm going to be making use of will be the following restriction. Here's a vertical asymptote at x equals 0, and here's a vertical asymptote at x equals pi. What we're going to do is grab this portion of the cotangent function and work with just that portion. So with that restriction in place, the function becomes one-to-one. It now passes the horizontal line test. So we can define the inverse tangent function. Inverse cotangent function. That'll be y is equal to one of two different notations that we'll see. So inverse cotangent of x, also known as the arc cotangent of x. This is equivalent to the statement that the cotangent of y is equal to x. Now y is taking on the role of the angle, which means that y is going to be in between 0 and pi, and x is taking on the role of the ratio, which can be any real number. Now to actually evaluate an arc cotangent function, you should be aware of how to set up appropriate triangles for it. So expect to see the 30, 60, 90 right triangle, as well as the 45, 45, 90 right triangle from time to time. Now for the other two inverse trigonometric functions, we need restrictions that are going to make them one-to-one. Now with that in mind, what I'd like to do is reference back to the reciprocal of the secant function. The reciprocal of the secant function would be y equals the cosine of x, and the domain restriction that we're using for y equals the cosine of x is that x is allowed to go from 0 to pi. To generate the secant function, we put a vertical asymptote at the x-intercept, and we come in and boop, and boop at those 2 points. As long as the cosine is 1-to-1, the secant will be 1-to-1 as well. So the restriction that we use for the secant will be the following. X is allowed to be between 0 and pi, but it's not allowed to be equal to pi over 2. The reason that it can't be equal to pi over 2 is due to the fact that there's a vertical asymptote. Now for y equals the cosecant of x, we will call back to y equals the sine of x. The domain restriction that we used for the sine of x in order to make sure that it was 1-to-1 was from negative pi over 2 to positive pi over 2. Now to generate the cosecant function, we put a vertical asymptote where it touches the midline, come in from infinity and boop, come in from infinity and boop. That will still be a one-to-one function. So the restriction that we use for the cosecant will be the following. That'll be from negative pi over 2 to positive pi over 2 with the omission of x equals 0. The reason that we omit x equals 0 is, once again, there's a vertical asymptote there. Now the definitions of these will be hopefully relatively straightforward. If I say that y is equal to the inverse secant of x, or the arc secant of x, this is equivalent to saying that the secant of y is equal to x. Y is now referring to the angle, so the angle will be anywhere in there. Y is in the closed interval from 0 to pi with the omission of pi over 2. And x is in either negative infinity to negative 1 or 1 to infinity. Similarly, if I say y is equal to the inverse cosecant of x, or the arc cosecant of x, this is equivalent to saying the cosecant of y is equal to x. Y is now referring to the angle. So we'll say that y is in the closed interval from negative pi over 2 to pi over 2 with the omission of 0, and x, which would be referring to the range of the original cosecant function, will be in a similar boat as the secant. Now with those things in mind, very similar to what we did for the arcsine, arccosine, and arctangent, this means that there are certain quadrant restrictions associated with all 6 of our inverse trig functions. So we'll call this the quadrant restrictions. The arcsine was restricted to be between negative pi over 2 and positive pi over 2. We refer to that as a quadrant 1 and quadrant 4 restriction. The inverse cosine had to be between 0 and pi. The inverse tangent was in between negative pi over 2 and positive pi over 2. The inverse cotangent was from 0 to pi. That was between 2 asymptotes. The inverse secant, we just did the same thing as the cosine. And the inverse cosecant, we just did the same thing as the sine. So the general rule that you're going to be looking for is the 2 quadrants that you're going to be using for each inverse trig function will be 0 if the ratio is positive, and the quadrant right next to it where that ratio winds up being negative. For example, the cosine is negative in quadrant 2, the sine is negative in quadrant 4. Now the 2 confusing ones are going to be the tangent and the cotangent, so unfortunately you'll have to just remember the in-between 2 asymptotes for those. The alternative would be to remember that there's 3 in each, and if you can remember sine, cosine, tangent, cotangent, secant, cosecant. So they alternate back and forth with the exception of going cotangent to secant. Now, there are no inverse cosecant, inverse cotangent, or inverse secant options on your calculator. So these are going to obey certain reciprocal identities. However, when we talk about the inverse trigonometric functions, the ratio is the thing that you're inputting. So, for example, the cosecant and the sine are reciprocals of each other. The way that this works is that the inverse cosecant of a number will be the same as the inverse sine of the corresponding ratio. In both of these cases, if this is an angle theta, sine would be opposite over hypotenuse, and cosecant would be hypotenuse over opposite. So this would be the picture associated with that. For the inverse secant, that's the reciprocal of cosine, so it's going to work the same way. And the picture that we have associated with this is that cosine is adjacent over hypotenuse, secant is hypotenuse over adjacent. Now, cotangent is going to work a little bit differently because its restriction is different than the tangent. They go to different negative quadrants. So if the ratio is positive, then it works the same way as the others. It'll be the inverse tangent of 1 over x. But if the ratio is negative, the inverse tangent is going to give you a negative angle whereas the inverse cotangent should be giving us a quadrant 2 angle. We would need to chase the angle from quadrant 4 to quadrant 2. The way that we do so is by finding that inverse tangent and then adding a half rotation to it.